In today's video, here is a nice problem. It's coming from the Japanese Mathematical Olympiad, edition 2009. Here is the following setup. Our goal, we are going to determine all n as a positive integer satisfy this condition. So we get 2 to the n plus n divides e to the n plus n. In the other word, e to the n plus n over 2 to the n plus n is an integer, okay? So in fact, this is very nice and interesting problem. So you guys, you can give the hands to this problem if you would like to. So notice here, as we know, we are going to divide this one into two cases. When we get n is a odd, when we get n is a even, okay? Starting with the oddness, now let's get into this one. So let's set, we get k equals as an integer. So I'm going to multiply, so crossing the multiplication, so get here. So we get k is multiplied by 2 to the n plus n, which equals e to the n is the same as 2 to the 3n plus n, okay? With the first case number 1, n is an odd, okay? So if n is an odd, I'm going to extract n out of this one. So we get n minus number 1 factor n. It's more simple because we get k is multiplied by n. We get n is multiplied by number 1. Also, I'm going to move over 2 to the n is multiplied by k to the right side and take it as a common factor. So I get 2 to the n factor 2 to the 2n. This one is multiplied, this one is give us this one minus k. On the left hand side of this equation, we get n divides left hand side of this equation, which means n divides the right hand side of this equation. So I'm going to reduce this one to mod n. This one is congruent to 0 mod n. Okay? Since n is odd, which means n cannot divide 2 to the n, which means n divides this one. Okay? It's more simple. N divides 2 to the 2n minus k. Okay? According to the divisibility statement, we get 2 to the 2n minus k equals m is multiplied by n, which means this one is a multiple of n, okay? So where is the m? Is a some natural number, okay? Consequently, we get k equals 2 to the 2n minus nm, okay? So I get here a nice expression here. Now I'm going to take this value of k and insert it back into the original equation. So I get the following. I get 2 to the 2n minus nm factor 2 to the 2n plus n, which equals 2 to the 3n plus n. I'm going to distribute this one out. I get 2 to the 3n plus n is multiplied by 2 to the 2n minus nm is multiplied by 2 to the n minus n square is multiplied by m, which equals 2 to the 3n plus n. So I will have a lot of cancellation here. This one is going to be cancelled out with this one. Then dividing both sides by n, I will extract a nice formula here. I get 2 to the 2n minus m is multiplied by 2 to the n minus nm, which equals number 1, okay? I'm going to move over these two terms to the right and move over again number 1 to the left and take m as a common factor, okay? So I will get 2 to the 2n minus number 1, which equals m factor n plus 2 to the n, okay? So I will get m equals 2 to the 2n minus number 1 all over n plus 2 to the n, okay? It's more simple. So if you take a look up here, since m is an integer, which means this one is an integer as well. So I'm going to use a nice trick here. So I get 2 to the n, I get 2 to the 2n minus n square plus n square minus number 1 all over n plus 2 to the n. I'm adding n square and minus n square because I want to construct a difference of two squares here. So I get 2 to the 2n. I'm going to factor out on the form of the product. I get 2 to the n minus n factor 2 to the n plus n square minus number 1 all over n plus 2 to the n. I'm split this one into two parts, two fractions. I get n plus 2 to the n. Okay, this one will be cancelled out with this one. I will be left with 2 to the n minus n, which means I get m equals 2 to the n minus n plus n square minus number 1 all over n plus 2 to the n. Okay, we get the left hand side of this equation is an integer or natural number, is the same thing. This one also is an integer, which means this one also is an integer. So this one is an integer, so which means if n equals 1, I got also this one integer, because n equals 1, it gets 0 in numerator. N equals 1 here, I get 1 plus 2, which is 3. I get 0 over 3, which is an integer. Okay, so now if n is superior equal to 3, what's gonna happen? Always you get a numerator is superior equal to the denominator, which means I get here n square minus number 1 must be superior equal to n plus 2 to the n. Okay, so I get here n square superior equal to 2 to the n plus number 1. I'm taking number 1 to the right. This one, it's clearly is a contradiction. Okay, because if n equals 3 here, I got 9. If n equals 3, I get 8 plus 3, which is 11, plus 1, which is 12. So we get here 9 is bigger than 12, which is impossible. Okay, this is contradiction. Impossible. What does mean impossible? Which means you have only one solution, which is n equals 1 if n is odd. Okay, so we get only one solution for oddness. Now let's get rid of this one, move over to the evenness. Now in this case, when we get n is even, you will have a different thing here. Okay, so now at this time we are going to assume if n is superior equal to 8, what's gonna happen here? So if I'm going to do that, so this one 2 to the n is always a congruent to 0 mod 2 to the 8. We know 2 to the 8 equals 256. Okay, also 2 to the 3n, also 2 to the 3n is a congruent to 0 mod 2 to the 8, which is 256. Okay, reducing the equation to the mod 256, so I get here this one 0, this one 0, so I will be left with k is multiplied by n, which is a congruent to n mod 256, or 2 to the 8 is the same thing. I'm going to move over n to the left and take it as a common factor, so I get here n factor k minus number 1, which is a congruent to 0 mod 2 to the 8. Okay, and then remember, so now I'm going to keep this nice expression. I'm not going to say anything now, because we need to prove k minus number 1 is an even first. Already n is an even, the product is an even, which means each term of this product is going to take a nice form expression. We are going to create a nice expression for each term of this product, but after proving k minus number 1 is an even. Okay, let's do that. So I'm going to do that by the way of contradiction. So by the way of contradiction, suppose if k minus number 1 is an even, which means k is an odd, I'm going to assume k is an even. Okay, at the end we will find k must be odd, not even. Okay, so what to do here? If this one if k is an even, we know already these two terms is even, because even is multiplied by even is going to give us each side of the equation, it will be a multiple of 4. So here, so I get 2 to the 3n plus n, which equals k is multiplied by 2 to the n plus n, is a congruent to 0 mod 4, as we discussed before, because we know this one is an even, this one also is an even, which means it will be a multiple of 4. But this one, based on this assumption that we have, Okay, it's not true yet because we are building our proof based on this assumption. Okay, so which means this one, it will be a multiple of 4. So we get 2 to the 3n plus n, which equals 4, is multiplied by c. What is a c? Is a some integer or some natural number. Okay, I'm not going far away from this one. I'm simply going to insert this one into the previous equation. So we get the following. I get 4c, which equals k is multiplied by 2 to the n plus n. Okay, also if you take a look up here, I'm going to extract n. So we get n equals 4c minus 2 to the 3n. Taking this value of n, insert it back into this one here. So I get k is multiplied by 2 to the n plus 4c minus 2 to the 3n. Okay, what to do here? I'm going to take 4c to the other side. So I get 4c factor. Get this one will be multiplied by number 1, but this one will be multiplied by minus k. Then taking 2 to the n as a common factor for this one, because I get 2 terms which is a power of 2. I'm going to take 2 to the n as a common factor, which means I get 2 to the n factor. So this one will be multiplied by number 1. This one will be multiplied by 2 to the 2n. Everything is multiplied by k. Okay, I'm going to flip this one and this one. I'm going to divide both sides by number 4. Okay, then divide both sides of this equation by k. So I get the following expression. I get c is multiplied by 1 minus 1 over k, which equals 2 to the n minus 2. Okay, factor 2 to the 2n minus number 1, like this. Also, I'm going to put this one c inside of this one. So I will have the following expression. I get c minus c over k, which equals 2 to the n minus 2 factor 2 to the 2n minus number 1, like this. Okay, so I have extracted a nice formula here. What do you know about this expression? We know c is an integer. We know the right answer of this equation is an integer, which means this fraction must be integer as well, which means k is a multiple of c. So I get here c equals m is multiplied by k. What is it? M is a some integer or natural number, whatever it is. Okay, so I'm going to take this value of c and insert it back into this one. Okay, c will be replaced with mk. C will be replaced with mk and will be cancelled out with k. Will be left with m. At the same time, I'm going to take m as a common factor. So get m factor k minus number 1. So this one equals to this one, which equals 2 to the 2n minus 2 factor 2 to the 2n minus number 1. It's more simple. Okay, so I get this nice formula, but k minus number 1 must be odd. If k minus number 1 is odd, it's going to take this term, because we have only the product involving the power of 2 and the odd. This odd is going to take k minus number 1. The other one is going to take m, which is the power of 2. So now I get the following equation system. I get m is going to take the power of 2, which is 2 to the n minus 2. The second equation, I get k minus number 1, which equals 2 to the 2n minus number 1. Okay, cancel out this minus number 1 from both sides. So I will be left with k must take this term, 2 to the 2n. Also, m equals 2 to the n minus 2. What to do here? I'm going to take this nice value of k and insert it back into the original equation to see what's the new expression. Okay, so we already found k equals 2 to the 2n. I'm going to replace it into the original equation. So I got the following. K will be replaced with the power of 2 to the 2n. So I get 2 to the 2n factor 2 to the n plus n, which equals 2 to the 3n plus n. I'm going to distribute this one out. I get this one is going to multiply by this one. I get 2 to the 3n plus n is multiplied by 2 to the 2n, which equals 2 to the 3n plus n. It's more simple. This one is going to be cancelled out with this one, and it will be dividing both sides by n. So finally I get 2 to the 2n, which equals number 1. Because you get n here, we get n here. So this one implies n equals 0. If n equals 0, which means k equals 1. It's impossible, it's a contradiction. Because we have chosen k is an even. Then we found out k it was odd. Okay? If k was odd, which means if k equals 1, which means numerator equals to denominator, which is impossible, which means a to the n plus n, which equals 2 to the n plus n, and will be cancelled out. I will be left with 2 to the 3n, which equals 2 to the n. It's clearly, it's impossible. It's a contradiction. So this one will be provided if n equals 0. If n equals 0, we'll have equality, which is impossible because we are dealing with positive integers. Okay? And also we get k equals 1. It was even, not odd, because based on the previous assumption that we have. What we have contradiction? We have contradicted our assumption, which means k cannot be even. K must be odd. Okay? Now let's get rid of this one and move on to the original problem. Now at this time we are going to continue working on this one. Now we get k was odd, which means k minus number 1 is an even, n is an even, which means both sides of this product, which means each of the term of a product is going to be written on this form. N is going to be written as 2 to the a is multiplied by a, and k minus number 1 also is going to be written on the form of 2 to the j is multiplied by b. This is one is an odd, b is an odd. Okay? Because we get this term, we get 2 to the 8 as a divisor, divides this product, which means both terms of this product are even, which means it's going to be written on this form. Okay? Now let's take these values, and also remember we are dealing with n is super equal to 8 based on assumption that we have. This one is going to be by the way of contradiction also. Okay, we are proving we have no solutions above this point. Okay, I'm going to take these both solutions and insert them back into the original equation, so I get the following. K will be replaced with 2 to the j is multiplied by b plus number 1 factor 2 to the n will be replaced with 2 to the a is multiplied by a plus 2 to the a is multiplied by a. Be careful when you replace n with this power of 2, because you will have a lot of confusion in the exponent here. Do it carefully. So this one 2, 3 is multiplied by 2 to the I is multiplied by a. Okay? Plus 2 to the a is multiplied by a. So now I'm going to distribute this one out. I will have the following expression: 2. This one will have the same base. I get 2 to the 2 to the I is multiplied by a plus j, because I have the same base, number 2. Then it will be multiplied by b. Plus the second term, I will have 2 to the a plus j is multiplied by a b, because we have the same base 2, and the exponent a plus g is multiplied by ab. Plus the third term. The third term, it will have the same number itself, 2 to the a is multiplied by a, plus the last term, which is 2 to the a is multiplied by a. It's more simple. Everything equals to this one. 2 to the 3 is multiplied by 2 to the a is multiplied by a, plus 2 to the a is multiplied by a, like this. This term, it will be cancelled out with this term. Then take this term and move it over to the right and take it as a common factor. At the same time, I'm going to take b and 2 to the I plus j as a common factor as well for the left hand side of this equation. So I get the following. I get 2 to the I plus j. Okay, factor this one, it will have 2 to the I is multiplied by a plus j minus I minus j plus a is everything is multiplied by b, because both of them are having b as a common factor. For the right hand side of this equation, I get also 2. For the right hand side of this equation, I get this term is going to be moved over to the right and take it as a common factor. So I get 2 to the 2a is multiplied by a factor 2 to the 3 is multiplied by 2 to the a is multiplied by a minus 2 to the a is multiplied by a minus number 1. Okay, I will have some simplification in exponent, and also I'm going to divide both sides by e plus j here. Also I'm going to take this term and divide it by this term. Let's write this one on the left hand side of this equation first. So I get 2 to the 2 to the a is multiplied by a minus I minus j factor this term, which is 2 to the 2ia. Remember here, because here I get 2 is multiplied by 2 to the I, which is 2 to the I plus number 1 is multiplied by a. This is everything in exponent now. Okay, minus number 1, which equals this term. This term is going to be 2 to the 2a is multiplied by a. This g was cancelled out, minus a plus a. It's everything, it was multiplied by b. Okay, if you take a look on the left hand side, if you take a look on the right hand side equation, it's an integer because the exponent is positive. This exponent is strictly superior than 0 because this one is bigger than this one, which means this one is integer plus another integer, which is multiplied by another integer, which is integer. But the left hand side equation, since the right hand side equation is integer, which means the left hand side one must be integer as well. This one is definitely is an integer, exponent is positive, minus number 1. But the problem, the left hand side equation is even because I have a power of 2. But the right hand side equation is an odd because we get this one is an odd plus even, which is odd. Odd is multiplied by odd, which is odd. This is odd. This is even. It's clearly, it's impossible. What does mean impossible? Which means we have no solutions if we have n is even above n is superior to 8, which means the only solutions that we get n equals 2 and 4 and 6. Okay, you guys, you can check that, you will find them, all of them are satisfied this fraction, which means this one is an integer. Okay, so I have done this problem. Thank you, bye.